Assalamualaikum. My name is Abdullah bin SHAMSUDIN, ID number 2021-2065-1A.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad RAZIN bin ZAHARUDIN.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ZULHAZMIE bin Muhammad Isa. My ID student numbers is 2021877262. Assalamualaikum warahmatullahi wabarakatuh, and I will introduce myself again. My name is Muhammad ZULHAZMIE bin Muhammad Isa, and our group will present about the chapter 4, atomic structure and energy level in an atom.
First off, let's take a look at the models of an atom, which is the pivotal element that gives rise to a better understanding of how things work in this world. And this is just a simple, I'm going to try to make it as simple as possible for everyone to follow. Currently, the model that is still in use is Erwin Schrödinger's quantum model that he had proposed back in 1926. But before that, scientists had come up with different ideas to how an atom should be interpreted, starting with a simple sphere. In 1903, John Dalton submitted his idea of how atoms look like, which he had stated in his theory that atoms are indivisible, which is partly correct. And long after that, in 1904, J.J. Thomson had come up with his plum pudding model, while in 1911, Ernest Rutherford discovered some particularly interesting properties of atoms. So he came up with his nuclear model, and shortly a few years later, Niels Bohr modified Rutherford's idea and proposed his infamously planetary model for an atom. In the discovery period of 1900s, Thomson's, Rutherford's, and Bohr's model seems to be closely related than that of the other discovery. So let's take a look at them. Let's start off with J.J. Thomson's plum pudding model, which he had proposed in 1904. In 1897, J.J. Thomson established the idea of charge-to-mass ratio for electrons. And with his recent discovery, he proposed that an atom has positive charge scattered out in the regional space of the atom with electrons embedded throughout this region. With this idea, the atom can be said to be neutrally charged. To name his model, he had to analogically use a simple everyday item, and guess what? A plum pudding was chosen as the most suitable example. Next up, we're going to look at the nuclear model by Ernest Rutherford back in 1911. Due to the nature of human curiosity, Ernest Rutherford and his students, which is Hans Geiger and Ernest Marsden, not related to Ernest Rutherford, they performed an experiment that denied Thomson's model. The experiment was conducted by shooting alpha particles toward a thin gold foil, and having scintillation screens to detect where the shot alpha particles end up. The results are of course fascinating. They observed that some particles went straight through the foil, while some were deflected slightly and others are directly deflected backwards back to the emitter. Based on their observation, they explained that the particles that move straight are because the particles simply did not hit any positive charge. So this cancels out the scattering positive charge theorized by Thomson. The deflection that was observed gave out an explanation that the positive charge may be concentrated in the middle of an atom. So they postulated that nucleus contains a high central charge concentrated in a very small volume. The small volume then contains the bulk of the atomic mass, and the nucleus is surrounded by lighter and negatively charged electrons. And this is the result from their experiment, the planetary model of an atom. But there is some key weakness in this model. The fact that Rutherford postulated that electrons revolve at a very high speed around a nucleus points out that the electrons underwent a centripetal acceleration. According to Maxwell's theory, this acceleration would release electromagnetic radiation with the frequency that is the same as the revolving frequency of the charge. As the radiation occurs, the radius of the electron's orbit would steadily decreases while the revolution frequency increases, and this would lead to the collapse of an atom, And we could say that the atom has a self-destruct function. But we do not want that to happen, as we, which also consists of atoms, would perish if we use this theory. So, to counter this weakness, Niels Bohr combined ideas from Planck's quantum theory, photon concept by Einstein, Rutherford's recently discovered model, and Newtonian mechanics to develop his now widely accepted model of an atom. His model was simply based on hydrogen atom, and these models are mainly the product of the discussion about the stability of certain orbits, the radiation emitted when electrons transition from higher to lower orbit, and the size of an allowed orbit inside an atom. He stated that to have a stable orbit, the electron must be in a stationary state where it doesn't emit energy even when accelerating to preserve the amount of total energy for the atom. If an electron needed to transition from higher to lower energy stationary state, there is going to be a form of radiation emitted by the electron in form of light, which has photons, and the frequency of which the emitted radiation relates to the atom's energy change. The energy of incident photon can be absorbed only if matches difference in energy between allowed state and the higher energy state occur. And lastly, the orbit size. The size of the allowed electron orbit is determined by the electron's orbital angular momentum shown by the equation, which directly explains that it is dependent on the quantum number of the orbit of which the electron is currently in, the electron speed in its orbit, and the orbital radius of the atom. So, what can we deduce based on my simplest explanation? Well, the first one is that the interpretation of atomic models is always advancing even in modern world. But the general positioning for the protons, neutrons, and electrons are, as of now, is that neutron and proton sits inside the nucleus of an atom, while electron, they sit outside the nucleus inside the phase region.
The part that I will cover in this chapter is emission and absorption line spectrum of hydrogen gas. First of all, what is emission spectrum? Emission spectrum is a spectrum of radiation emitted by substance that has absorbed energy. Atoms, molecules, and ions that have absorbed radiation are called excited. These excited atom, molecules, and ions, it will leap from lower to a higher energy level and emit radiation when it returns to its original state, where from the higher energy to a lower energy level. Meanwhile, an absorption spectrum is just the opposite of what the emission spectrum do. Line spectra is the emission spectra of atoms in a gas phase that emit light at only a specific wavelength with a dark space between them. Each element has its own unique line emission spectrum. Because of this characteristic line in an atomic spectrum, they are used to identify an unknown atom. Line spectrum of hydrogen gas. Hydrogen molecules dissociate when electric discharge was passed through gaseous hydrogen. Subsequently, the energetically excited H2 atoms emit electromagnetic radiation of discrete frequencies, giving a rise to a spectrum. The series of hydrogen emission spectrum is known as the Balmer series. In 1885, Balmer showed that if spectral lines are expressed as wave numbers, then visible line of the hydrogen spectrum will obey the formula wave numbers equal to RH 1 per n square minus 1 per n square, where RH is the Rayleigh constant. Line spectrum of the hydrogen gas is the only series of lines in the electromagnetic spectrum that lies in the visible region of electromagnetic radiation. We can see it in this image. The next part that I will cover is the evidence of quantized energy level. In some systems, energy is quantized, which means that the system can only have a particular energy and not a continuum of energies, as in classical situation. Planck was able to appropriately characterize the scientifically known geometry of the black-body spectrum via oscillator quantization. That was the first demonstration that energy may be quantized on a tiny scale, and it earned him the Nobel Prize in Physics in 1918. This is one evidence that energy can be quantized. Next is the Frank-Hertz experiment. In 1914, James Frank and Gustav Hertz performed an experiment that demonstrated the existence of excited state in mercury atom. From this first-hand experiment apparatus, we can see that the electrons were accelerated by a voltage toward a positively charged grid. We can also see that past the grid was a collection plate held at a small negative voltage. At the end of this experiment, the value of accelerating voltage gave a measure of the energy necessary to force electron to an excited state. This is the Frank-Hertz data for mercury. From this graph, we can see that the sharp ending indicates that enough energy was taken away from the electron so that they could not reach the collector. The drop shown refers to the inelastic collision between the accelerated electron and the atomic electron in the mercury atom. We can also see that the sudden ending shown in the graph suggests that the mercury electron cannot accept energy until it reaches the threshold for lifting them to an excited state.
How fluorescent lamp work? Fluorescence work when collision in a hot gas of free accelerated electron with atom, typically mercury. Electrons are bumped up to higher energy levels and then fall back while emitting at 2 UV emission line. This effect also called photoelectric, which is emission of electron when electromagnetic radiation such as light hits a material. This is an example of inside of fluorescent lamp. Electrons emitted in this manner are called photoelectrons. Why is there a gas in fluorescent lamp? Gas is a conductor of electricity and the material in a tube that produces light. Gas is a mercury vapor. When the gas is heated by flowing electricity, the mercury atom vibrate and reach the plasma state. A fluorescent lamp or fluorescent tube is a low-pressure mercury vapor gas discharge lamp that uses fluorescence to produce visible light. What type of gas inside the fluorescent lamp? Gas that containing in fluorescent lamp is a gas that containing low-pressure mercury vapor. Besides that, noble gases are also found in fluorescent lamp. This is because noble gases such as argon is an unreactive element and often used in fluorescent lighting and discharge lamp. Why it is dangerous to break a fluorescent lamp? Fluorescent bulb or lamp contain a small amount of elemental mercury, typically between 2 and 5 mg. So when the fluorescent lamp is broken, the mercury vapor may be released into the air. The mercury released from a broken bulb is mostly in vapor form, and this is also called mercury exposure. So continue from the slide before, which is mercury exposure. Mercury exposure is very dangerous because the fluorescent lamp contains such a small amount of mercury, like I said before. However, even a small exposure can affect the developing brain and central nervous system in fetus and young children. So it is very dangerous for our child and the future. So is a broken fluorescent lamp usable? Recycling fluorescent lamp and other fluorescent bulb allow reuse of the glass. The fluorescent lamp can't be usable, but the glass can reuse, and the metal and the other materials that make up the fluorescent light can be reused.